Okay, so A is the event that 3 is chosen. All right. Find the probability that 3 is chosen. Express your probability in probability notation. Okay, so hopefully that's not too bad. So we probability notation, this is P of A, right? And then it's going to equal, and they want us in fraction form, so what's our probability basic formula? Denominator is total number of outcomes, numerator is. So you know it's 4, right? Yeah. Okay, so it's a total number of possible that that meet the criteria in the top, and then total number of choices in the bottom. So what? Oh, I thought it said it went in fraction. So what is 1/13? Anybody have it?
0.077.
Okay. Oh, that was it? Okay. So maybe because this was a little multiple choice, some of you got partial credit. All right, well, so everything else was on the assignment. You guys did really well, so I don't have to spend much time with that. Oh, is that the right one? Oh, that's the wrong question. There we go. I thought I went to that. There we go. This is the one. Okay. So age distribution for politicians. Accompanying table. A politician is selected at random. Here we go. So how would the complementary rule? Okay, so the complement rule looks at everything else, right? The not situation. So if we want, can't move this. Here we go. So how would the combination rule calculate this probability 50 years or older? So the complement is the not situation, right? So what's not 50 years or older? Under 50. So we talked about if we get the probability of everything else, if the total of all probability is 1, then the probability that we want will be 1 minus the probability of everything else. So this one, calculate the probability that the randomly selected politician is 50 years or older, then subtract that probability from 1. That's the complement. The complement is everything else, and so it's going to be the rest of the probability other than 1. So you're going to calculate the probability of everything else. No, that's not right. 50. Not 50 years or older. Yes, right, not. Okay, I just didn't read it fast. Didn't read it slow enough. Okay, yeah, so you want the probability of everything else, and if you take 1 minus that, you get the probability of the thing that you want. So let's use it. So we want 1 minus, how many total are there? 2, 19, 60, 101. And so we want 1 minus 9 over 101. So we take they'll use it to help us here. So 9 over 101 is, and then 1 minus that. Anyone got it? So 1 minus, which is 911. Good. Okay. All right. So complementation rule is under 70. So under 70 would be, if we use the complementation rule, it's going to be everything else. What's everything else that's not under 70? Under 70 would be these 3, right? And so everything else would be 70 and up. So now we're going to take that probability of what we don't want, which is all these 19, and do 1 minus that. So we're going to find the probability for 70 and up. calculate the probability that randomly selected politician is not 70 years old, not under 70 years old, then subtract from 1. And then they want us to do that. So we're going to do 1 minus. See, so the point is it's less work, right? It's a little bit, this one is hardly a difference, but like the first one we saw was less work. You know, adding up a small number of numbers is easier than adding up a big long list of numbers. So often the complement is a faster way to go by going indirectly. So we want a 19 out of 101, and then 1 minus that. Okay, questions on the complement rule? So what if we wanted the probability of 79 or younger? 79 or younger. Tell the person next to you what you could do. If you wanted the probability of 79 or younger, you want to do it the fastest way possible, what do you do? Is this all the quizzes? Do you have all the quizzes? '79 or younger, easiest way. Go. Let's see. Did you get it? Can you tell me? Yeah. No, right here. What's your name? Jessica. How would you most easily get the probability of 79 or younger? Huh? So we want the probability of 79 or younger, right? So we want probability of any of these situations. We want the easiest way to do it. So we want probability of any of those. Gina, did you get it? Mm-hmm. Tell me how.
You take the 80 and over, which is 2. 2 over 101. So 101 divided by 2. And then that would come out to 0.01020.
Don't worry about the numbers. Don't worry about the numbers. Go ahead.
So 2 divided by 101. And then 1 minus that answer.
Right. Right. So we're going to get the probability of 80 and over, which is everything else, which is the not, the complement, and take 1 minus that. Is that what you guys said? Yeah. Okay. Because the total of all probability is 1. If we were to total up all these and divide by 101, it would be 1. So then if you need a probability of any subset, then it'd be 1 minus the probability of the other subset of the complement, what we call the complement. Okay. So let's press on here. So we're going to go to chapter 6 next. And so we're talking about the exam. The exam is next week, right? So a week from Wednesday, okay? A week from Wednesday. So we got time. Okay, so normally distributed variables. So we've seen some things like this. These are ways of visually seeing the distribution of the data. Okay, so this was like a histogram or bar chart. This was a stem and leaf plot, and this is a dot plot. But they're all kind of showing us the same thing. They're showing us the shape of the distribution. The shape of the distribution. Okay? So when we talk about shape of distribution, we have to really be confident that we know what we're looking at on the horizontal scale and what we're looking at on the vertical scale. because that's always the same. And when you start seeing these distributions, those things aren't written down. You just see a curve, right? So you just see a curve like this one. You just see this curve. I tried. Something like that, okay? Not my best curve, but the best one I've drawn today. Okay, so you're going to see a curve like this. You won't see any numbers on either axes, and you have to look at that and know what you're looking at. So it's a matter of understanding, what does that horizontal axis mean, and what does it mean up and down? What does the height of the curve mean versus a position on the curve left and right? Okay, so maybe this is really important, so maybe take a second, see if you remember. We've talked about it before. Tell the person next to you, what is, in general, what does the horizontal, moving horizontally mean, and what does up and down mean? Okay, so this one, I'm kind of even just giving it to you in your face. But let's just tell the person next to you. So what do they mean? Yeah, horizon. That's the way to think. Horizon.
So you're standing up, you're vertical. And then you look at the horizon, it's over the line.
Okay, so horizontal. The horizontal, what does it mean?
The number of events.
The number of events. That's not correct. And what does that mean? Values of the variable.
So you have different variables.
Okay.
And then that's the best way you could probably organize them so that they look easy to read.
Do we have different variables here? More than one variable? No. What is a variable? What does that mean, a variable? A variable varies. A variable, that's why it's called a variable, because it varies. It takes on different values. It takes on different values. So they went to a bunch of households and they knock on the door and they say, how many TVs do you have? So they're at house number 1 and they say, we have 2 TVs. Now the variable is 2. They move to the next house and knock on the door and say, how many TVs do you have? They say 1. It's the same variable, it just took on a different value now. It was 2 before, now it takes on 1. Go to the next house and knock on the door. How many TVs do you have? 0. Okay, now the value of the variable is 0. Next door, knock on the door. We have 2. Well, now the variable is 2 again. So there's one variable, it's the number of TVs. It takes on many values. So that's why it's values of the variable. And the variable is the thing we're interested in. It's this number, that's the data we're collecting, right? It's the data we're collecting. It's this thing. This is prices of DVD players. That's a variable. As you go from DVD to DVD player, they have different prices. But it's one variable, the price of a DVD player. And then as we go from one to the next, we get all these different data values. Okay, so what's our variable here is DVD players, and it takes on different values. And then you go, just like a normal scale, you go greater from left to right. So over on the left, the value is less. And then as you move to the right, it's for higher values of the variable. Okay, so just like just a numerical scale. Okay, what about stem and leaf plot? Do we see that here? Oh, so no, what about vertically? Okay, so then vertically. Okay, so and what does that mean? So yes, frequency. Right, okay, so the variable's taking on different values. 1 TV, 3 TVs, 0 TV, 2 TVs. We're going door to door, right? So then we can take all our data and we say, what was the frequency of 2 TVs? What was the frequency of 3 TVs? What was the frequency of 6 TVs? So that's what we put up, right? So most people that we went to their house, how many TVs did they have? 1, right? So the most number of people, about over 30% of the people we knocked on their door, said they had 1 TV. What's next? 2, and then 3. So the height then, so that's going to be the same as the height of the curve. When you see these curves, you pick a value of the variable. The height of the curve at that point represents the frequency. If it's higher, it's a greater frequency. If it's lower, it's a lower frequency. So you see this curve right here, and you see, oh, right here down in the lower values was the highest frequency, and then as we go up at higher values is less and less frequent. Okay, same thing with a dot plot. You start stacking the dots up. The more dots you stack up, the more data, the more frequent it is on that value of the variable, on that particular value. All right, so what about this? Does this fit that pattern, the stem and leaf? Yeah, but it switched, right? So now our values of the variable are like running up and down this way, and our frequency is running out to the right. So if you were to turn it, now it's the same. Okay? And so again, we're going least value of the variable to greatest. All right? And so what range of values has the highest frequency? What range of values has the highest frequency? Right. This is the range 210 to when the variable takes on those values 210 to 214. That's where we have the most frequency. And so curve, right? So this gives a curve. And so then we talked about different shapes of curves, right? Different shapes of curves. Skew, right? We talked about skew. Is this one right skewed or left skewed? Okay, people are saying right. Okay, and so it's a little bit counterintuitive. Why? Because most of the data is to the left. So why is it called right skewed? Everybody remember? Why is it called right skewed if most of the data is to the left? So the key is the skew about the mean or the median? The mean. The median is down here closer to the most frequent values. It's because of these values over here on the right will pull on the mean this way. Right? So it's about where the mean is relative to the median or relative to the highest frequency. Our highest frequency of television sets is around 1 or 2, but because there's a few out here that have a large value, 5 and 6, that's going to pull on the mean, right? It's going to pull on the mean to the right, so it's right skewed. What about the next one? Symmetric?
Yes.
So is it symmetric? It's got a little skew. Which way? Left or right? Little left, right? A little bit left. Because you have, yeah, you do definitely have a left skew because you have these 4 data values instead of this 1 data value, right? So you definitely have a left skew here. Most of the data is here, but the mean is going to be lower than where most of the data is. It's a left skew. Okay, and then we get something here it's not really left or right skewed, but we have kind of what's called multimodal, right? So there's different places where the data is kind of grouping together. You kind of have a mode around 199. You have a mode here around 210. And you have a mode here at like 219. So this is called multimodal. Right? A mode being highest frequency. So we have 3 places of kind of highest frequency. Okay, important review. So like what we're going to be looking at is we'll just see something like this. That's all you'll see. What does the horizontal mean? Just the values of whatever variable we're talking about, right? And then the height of the curve. So if you pick a value of the variable, boom. The height of the curve means? The frequency. How frequent that variable, that value showed up. Okay, so common distribution, just like this, common distribution shapes. All right, so we talked about left and right skewed, multimodal. All right, so the normal distribution is this one, bell-shaped. This is the normal distribution. That's what we're going to talk about now. Lots of things in life, lots of variables in life. When you take lots of data, you get a normal distribution, but not all, okay? Not all. But like, for instance, exam scores. Exam scores is the perfect example of normal distribution, like the ACT or the SAT, college entrance exams. You get thousands and thousands of people that take these, and if they put their data in a distribution, it will be normal, okay? It'll be a normal distribution. Heights. Height is normally distributed. Okay, so here, this is heights. And they're making each one of these bars in our histogram. Each bar is like a 1-inch range, okay? A 1-inch range. And then, like I've been doing, they're matching a curve to the heights of the bars. So let's look at this particular height range here, from 67 to 68 inches tall. Has a frequency of 0.0735 or 7.35%. So 7.535% of all, I don't know if it's all people or certain subgroup, but 7.35% of people their height is between 67 and 68 inches. Okay, and so that relative frequency is the 0.0735. Okay, so now I want you to notice something. If you looked at this thing they've shaded, see how they shaded that blue rectangle there? What's the width of that rectangle? 1, right? That's 1. And what's the height of the rectangle? That's our frequency, right? 0.0735, right? So the height here, so that relative frequency, notice that relative frequency is also the area shaded there in blue, right? Because what's the area of a rectangle? Area of a rectangle is base times height. So if we took the width of the rectangle times the height, 0.0735, you get? Okay, so there's this relationship. It's this equivalence of, there's an equivalence of frequency and area. Okay, so a equivalence between frequency and area. That the area of that shaded region, 0.0735, is the same as the frequency for that range of the data, for that range of the variable. So what we're going to start thinking about is areas under the curve, and I'm laying the foundation for the fact that area under the curve, the value of area is equivalent to relative frequency. So can you explain that? What's your name? Can you explain what I just said? Back. So let's look at. All right. So it says here's this female. So this was female college students. So the area under the standard normal curve with parameters. So our population mean is 64.4. Okay, standard deviation is 2.4. That lies to the left of 61 is 0.0783. So here's 61 inches tall. And so left would be heights less or greater than 61. To the left would be less or greater? Less. These are heights less. And so what we can do is we can say, all right, if we add up these areas here, so yeah, so no, let's just do it from the table, right? So let's do it without area first. So what's the frequency of female college students who have a height 61 or less? So what's the frequency of female college students that have a height 61 or less? Figure that out, okay? Oh, it says right here. But yeah, go ahead and do it. So we're going to confirm that it's this number right here. How do they get this number? 0.0783. From the table you get 0.784. Okay? That's from the table, right? The table reflects each individual. So the table reflects this. When you added that, you took that first number, what, 0.0757? That's this area right here. And then you took 0.0454. That's this area right here, right? So the table reflects kind of adding up those, was it 4? 5, okay? So there's this little area here, and then this little area. Okay? So why is that a little bit greater than the actual probability? Can you see? We talked, so the actual, this is adding up those individually. The actual probability less than 61 is based on the blue curve. It's based on the blue curve, and it's the area underneath, so I'm going to make it red, so that the area underneath the red curve, so the area in this region here. So do you see why our sum total of those relative frequencies is a little bit greater than the actual probability? Can you see why? Why is it? Yeah.
Is it because the curve shapes the corner of those data numbers off?
Right. Right. So using the area of the actual rectangles, we get too much, right? We get a little too much area. These corners are sticking up a little too high. They're declaring this based on the actual curve and the area truly underneath the curve. Okay? By adding up the individual data values in the table, you also get this little extra area from the corners of the rectangles that stick out. Okay? But the point is that we don't have to do it by the rectangles. We can do it by areas under the curve, right? So the whole point is that the area under the curve, that area under the curve is the 0.0783. That's the same as the frequency that the variable was less than 61. So the whole point here is that area value of area is the value of relative frequency. Okay, does it make sense? That was the task I gave you, to use the table to find it. Did you do that? Okay, what did you get? Okay, so just something went wrong with your math. So we were adding up, should have added up these 5 values. Right there. So just something you punched wrong or something. When you add up those 5 values, you get 0.0784, right? Is that?
Yes.
Okay, yeah, you just punched wrong. And that's the frequency, relative frequency for under 61, okay? And so we're seeing now that that is equivalent to the number of area under the curve for that range of the variable. So if we're doing less than 61, we get this area under the curve. I shaded in red. It's virtually equivalent to that. And if so, and it would be equivalent if we were measuring to a lot finer precision, like 1/10 of an inch, and all these rectangles were 1/10 of an inch wide, and we had lots and lots of data, then these two numbers would converge on each other. They'd be the same. So if we sliced our ranges a lot smaller, then what we would have all these skinny rectangles, right? Much skinnier rectangles, and they would do better and better at matching that area. Okay. But we need lots of data for those two values to converge. But we see it's really, really close, right? Even here, just with 1 inch data ranges, it's really, really close. Okay, but the big point is area under the curve is showing us relative frequency. So we're going to practice that. Okay, so here's 3 normal distributions, and they're on this scale where we don't know what the value of the variables is, but the first one has a mean of -2, standard deviation 1, then mean of 3, standard deviation 1/2, mean of 9, standard deviation 2. So if I were to shade this area right here, and then if I were to shade this area right here, so call this one A1, and call that area right there A2, and then A3. So what do the values of A1, A2, and A3 represent? So have a conversation, okay? What do the values of A1, A2, and be as specific as you can. So that area is a number, right? That area right there is a number. What does that number represent or mean? That area right there is a number. What does that number represent or mean? Same with A3, okay? Talk. Everyone's talking to somebody, okay? Go.
Second one, you want 4.5 or is it 4?
Yeah.
The one in red.
I'm trying to show just 4, right? So the idea is on these, 4 is the key number on those. Okay. So what does A1 represent? Tell me your name. Dan? What do you think? What does so if A1 is that area right there, what does it represent for our purposes? What is A1?
It represents like the frequency between -6 and 1, or values of -6 to 3.
Okay. So it's really not about the -6 here. We didn't talk about that, but these distributions are thought to, when you do the curves, you just think about it going on forever. Okay, so on either side. So it's really mostly about how can we just frame that in terms of -3? So that's how we want to frame this one, just in terms of -3. So what does A1 mean in terms of -3? But yeah, everything else was great. So how can we just tweak that a little bit? Yeah.
So the relative frequency of values under -3.
The relative frequency of values under -3, less than -3. That's what it is, okay? So we think of these, theoretically, these curves then, we think of them going on forever. So something like that would be, that area would represent the relative frequency of the values of the variable being less than -3. Okay, how about A2? Tell me.
So it's the relative frequency of values over 4.
Right, for that distribution, right? So we should have said for the green distribution in the first one. For the green distribution, that's the relative frequency of values under -3. And so now for this one, for the red distribution, it's the relative frequency of values above 4. Okay, and then how about A3? What does A3 represent?
The value between 8 and 12, the relative frequency of the values.
Okay, so for this distribution, for the tan distribution, the relative frequency of values between 8 and 12 is the same as the value of that area. Okay, does it make sense? Yes, please.
So basically, whenever you are asking us to figure out what areas represent, it's going to be about relative frequency?
No, yeah, all semester we're going to be just doing. I'm not going to ask that question again, but it's going to be just come up all semester. That it's going to be the other way around. It's going to be, what's the relative frequency or the probability for this range? Then we're going to go to the table and we're going to look up the area, and we're going to answer that question. So it's like the other way around. Does that make sense? So this is some distribution. We're interested in the relative frequency from 8 to 12. Well, if we knew that area, we would know that relative frequency. We're going to have a table that gives us that area. We're going to go into the chart, and we're going to figure out how to get that amount of area, and that's going to represent our frequency from 8 to 12. Does that make sense? Does that answer your question?
I probably need to do one.
So we're doing them all semester. This is the rest of the semester we're going to be doing this. All semester long, okay? So we'll get lots of examples. Okay, so you practice. So we'll do the first one together and you practice. Okay, so the area under the density curve that lies to the left of 10 is 0.654. What percentage of all possible observations of the variable are less than 10? What do you think? Paul? The area under the density curve that lies to the left of 10 is 0.654. What percentage of all possible observations are less than 10? 65.4%. And what percentage of the possible observations are at least 10? And you don't have to do it in your head. Just how would you find that? What would you do?
You just look at 0.654 and then know that one is the highest that you can get.
Okay.
So and it's over 0.5, so it's got to be greater than 50%.
How would you get the number? At least 10. Less than 10 is 0.654. Then what is our percentage greater than 10? The complement thing, 1 minus 0.654. Okay, so then where on this scale is 10? Where would you guess 10 is on this variable scale? So we get the values of the variable here. Is 10 like down here? So I'll give you here, choices here. So A, B. So where is 10 relative to values A, B, C, and D? Okay, talk. Where would you put the value 10 along the scale A, B, C, D? And it could be between. So you could say between B and C, or to the left, to the right of D, to the left of A. Doesn't have to be one of those four. Yeah, exactly. So I heard. So go ahead. What were you saying?
Well, I was guessing C because if you have 10,
Uh-huh.
and over half of your data is to the left of 10, then 10 can't be in the middle, and it can't be really far left because then it's not 65% of it.
Did you hear what she said? So if to the left of 10 is 65% of the area, it's more than half. Between C and D. What do you think? So first of all, is it going to be to the left or right of the middle? To the right of the middle. So then the question is, how far to the right to estimate about 65%? C might be a little too far over, because 65 is just a little greater than half. So maybe something like this. But if you said C, that's by far, if you're picking one of those four, by far the best. So maybe right about there is 10. So then we see, what's that?
No, we said between B and C.
Right, but definitely to the right of the middle. So that area right there is, if this is 10 right here on the variable scale, that's 10, then that area is in this distribution, okay, only in this distribution, 0.654. I can't write today. Okay, and so then this area is, and then this area over here, whatever 1 minus, right? This is the complement principle. Everything else, right? Everything else, 1 minus 0.654. And 10 is right there, or some really close to there. Okay, so on your sheet, I want you to do 7, 8, and 10. Okay, so these three. You answer the questions as asked, and then make the sketch like we made the sketch. Okay, so you're going to answer the questions as asked, A and B for each one, and then you're going to just estimate with a sketch like we did. Where is 15? Where is 30 and 40? Where is 8? Okay. Which one am I doing? Which one should I do? I'll do one of those three.
Second one.
People are saying the second one. Agree? We have a consensus? Sweet. Okay. So between 30 and 40 is 0.832. So first of all, what's the percentage of all possible observations of the variable that are less than 30 or greater than 40? So what lies between them, 30 and 40, is 0.832. Now they're saying what's either less than 30 or greater than 40? What does it have to be?
8.4.
So it's either or, right? Either or. Either or. Could be less than 30 or greater than 40. So it's just the complement of that. It's everything else. Because everything else that's not between the two is on the outsides of that. So if you say either or, you're saying everything on the outsides of that, that's going to be 1 minus your 0.832. And the question is, we have to now land a 30 and a 40 that looks about like, what, 83% of all the area under the curve. So you don't know where that is, left or right. Does that make sense? But as long as you are showing a great deal of it between 30 and 40. So like, for instance, this, if I went like, I'll just make it small, like this, and this, that would not be 30 and 40. You see that? Why? Because that might be 10 or 15% of the data in between those. So it's going to be something that's showing something between 30 and 40 that's showing most of it. So just maybe that might be a little too much. And so we're just eyeballing. We're just getting that feel. It's not about being perfect. But would you buy that that's about 85% of all the area under the curve? Would you buy that? Something like that. Something like that is. So then our value of 30 on the variable scale would be here. And our value of 40 would be something like that. But you don't want just a sliver, and you don't want the whole thing. We're shooting for 83% of all that area under there between 30 and 40. So then your number, what number did you get for less than 30 or greater than 40? 16 points or something?
It's 0.168, but you need to divide it by 2 because you have two
Nope.
sides.
What percentage of all possible observations are either less than 30 or greater than 40?
8.4%.
No. What does this set mean? Remember we talked about sets and events. What set is that? So remember we talked about probability and events. This is the event that you're either less than 30 or greater than 40.
16.8.
Yeah. See, all this, if I shade all this red, all of the red, both sides, is the event that they're asking about. Do you see that? Either less than 30 or greater than 40. So all that I've shaded in red is what I've circled in red. So that's the 16.8%. Would you buy it? Is it better, Gina?
Yeah.
It's not just saying what percentage of possible observations are less than 30. That's what you're calculating. You're just calculating less than 30.
Or greater than 40.
But this is one set put together. Yes,
Okay.
if the question was less than 30, it would be 8%. If the question was greater than 40, it would be 8%. But the question is all of that, less than 30 or greater than 40. Is that better? Yeah. So I see. So it's like, if it was the same question asked two different ways, then you're exactly right. It's 8%. But this is one set. This is one set. Okay, so now now we're going to talk about let's get standard deviation involved here. So consider two normal distributions, one with mean of -4, standard deviation 3, and the other with mean of 6 and standard deviation 3. Okay? Do they have the same shape, or are they centered, or true or false? True or false, they have the same shape. True or false, they're centered at the same place. So they have the same shape, true or false. What do you think? Is that a matter of the same shape? Is that a matter of the mean or the standard deviation? They have the same shape. Does it have to do with the mean? What does the mean have to do with? So if we're looking at a normal distribution, where's the mean? Where's the mean in the normal distribution? What? The middle, right? So the mean is, it's like in a normal distribution, mean, median, and mode are all the same. It's the highest frequency, and it's not skewed, right? It's the highest frequency, so that's your mode, right in the middle. And there's no skew, so the mean and median are all right there at the middle. So all three, mean, median, and mode are all the same. So mean is a matter of where the distribution is, where that center of that distribution is on the scale. So then shape is a matter of standard deviation. Let's go back to the previous screen and look at these different distributions here. So they all have different means, -2, 3, and 9, so they're in different places on the scale. But what do you notice about the standard deviation and the shape? For a larger standard deviation, what do we know about the data values? They're more spread out. So if they're more spread out, what about the frequencies of things? If data is more spread out, what about the frequency? Higher or lower? Lower, right? So if stuff is more spread out, then any given value of the variable is going to have overall is going to have a lower frequency, and then we see that, right? So for a greater standard deviation, stuff is more spread out, so then it has overall lower frequency. And then for a smaller standard deviation, means more consistency or less spread out. So what happens to the frequency then? Everything's crunched around the mean. All the data is crunched around the mean. So you have high frequencies. So you get this tall, skinny curve for low standard deviation. This is something in between, right? Something in between. Standard deviation is 1. So you have, so what happens? As the standard deviation goes up, what happens to the curve? As standard deviation increases. But no, the height, I'm talking about the heights of the curve, right? Flattens out, right? Because you're spreading out the data, so all the frequencies come down, right? If you crunch all the data to the middle, then the frequencies shoot up around the middle, right? And that's a lower standard deviation. So for a higher standard deviation, your frequencies come down. For a lower standard deviation, you pack all the data near this mean, frequencies shoot up. Okay, so how do we standardize for that? How do we normalize for that? You had to do it on your quiz. Z-score, okay? So Z-score. So for an X value of -2, or let's make it more interesting here. So let's look at an X value of -1 on this scale, 4 on this scale, and 10 on this scale. So we want x1 here, so this is like the x1 variable. So green is x1. Red is x2. And brown is x3, okay? So let's get the z-scores for -1, 4, and 10 on their respective scales, okay? Oh, no. No, not on the blue paper. Just, this is for your notes, okay? So get the z-scores for -1, 4, and 10 for variables x1, x2, and x3 respectively, okay? Respectively. And then compare your results. So can we do that fast? Anyone got x1? Exactly 1? Perfect. Okay. x2. 2? And what about x3? Okay, so it's going to be the -1 minus the mean over the standard deviation. You got it? Okay, so which value, x1, x2, or x3, is the highest value relative to its distribution? What's most out of the norm? What's the greatest, has the most deviation from the norm? Which one's the greatest? Right, so this value of 4 is, if these were like test scores, the student who got 4 on test 2 did the best, right? Because we can compare. Now we're apples to apples here. We can compare z-scores. All right, so now we're going to talk about area then. So let's do area to the right. So which area to the right is greatest? Which area to the right is the greatest? Since this one, this value, 10, is closest to its mean, then there's the most area to the right, right? This is a 1/2 standard deviation above, so therefore that's the most area, and which has the least area to the right? X2, all right? So there's now, so since Z standardizes things for us, it standardizes the areas as well, the frequencies, okay? So it doesn't only standardize values, but now it will standardize areas. So anytime that you're 1 standard deviation above the mean, so let's change these. So 1 standard deviation above the mean is -1. 1 standard deviation above the mean is 3.5. And what's 1 standard deviation above the mean here? 11. Okay, would you buy that? So I'm going to go from the mean, I'm going to go up 1 standard deviation, 1. From the mean, 3, I'm going to go up 1 standard deviation, that takes me to 3.5. And then from the mean, 11, I'm going to go up 1 standard deviation, that takes me to 11. Which area is the greatest? So -1 is 1 standard deviation above its mean. 3.5 is 1 standard deviation above its mean. And 11 is 1 standard deviation above its mean. And we're talking about now the frequency greater than each of those x values. The frequency, relative frequency greater, or the area to the right. Which area is the greatest? What do you think? They're the same. Yes, because they're all 1 standard deviation. All right, so if we were to find the z-score, look, if we find the z-score for -1, we would get 1. If we were to find the z-score for 3.5, what would we get? 1. If we found the z-score for 11, what would we get? 1. So they're all one more try, this area. So this is our normal distribution. This is our standardized curve. All of those x values I told you are exactly the same in terms of z-score. They're all 1 standard deviation above the mean. So all of those areas are equal to this area. All 4 of those areas are the same because they're all standardized to be exactly one standard deviation above the mean. So all 4 areas are equal. It's the percent of the data that lies greater than 1 standard deviation above the mean, which is the same for every normal distribution. For every normal distribution, if you want the percent of the data that lies greater than 1 standard deviation above the mean, it's going to be the same. Because remember, within plus or minus 1 is 68%. Remember that? 68% of the data lies within here. So what is that area that we've been talking about that they're all 4 the same? Well, if that's 68%, now here's your divide by 2. Okay? So if this is 68% of the data, then what is this black area right here? It's going to be the 1 minus 68, but then we just want to the right. So what is that? 1 minus 68 is? Is that 32? So then this percent is 16%. And what's this area right here? 16%. What about this one? 16%. What about this one? 16%. Okay. So that's why we can use a table to do this. If we take any normal distribution and then use the z-score, then we've got it in terms of standard deviations, and we can have a table that gives us areas for z-scores. And then that tells us our relative frequency in our distribution. We're going to do a lot of this, okay? We're going to do a lot of this. Okay, anybody have a question? So here, this is normal curve between A and B, got an area. If you standardize that on the standard normal curve, your z-scores, the area between the z-scores will be the same area, the same relative frequency as between your A and B on your curve.